Hello, everyone. Today, we're going to go through some of the cloud data engineering aspects, and I'm going to walk you through a couple of challenges, a couple of latest innovations, and how cloud data engineering is transforming businesses across globally, and what are some of the benefits that typically businesses would see in terms of moving into the cloud data engineering side of things. Mainly, the cloud data engineering it's also driving innovation by enabling organizations to manage data efficiently and cost effectively. So let's take multiple platforms that we have today. So we have AWS, we have GCP, we have Azure. We also have several platforms that are built on top of these different cloud platforms, like Snowflake, Databricks. One of the very good examples that we could also consider is Netflix as a very good use case. So organizations like Netflix, they basically exemplify the cloud data engineering's potential by delivering highly personalized content experiences to millions of users worldwide. And they also very efficiently manage the data streams by leveraging the cloud technologies. So you would have already known that the architecture for Netflix is it basically runs on that's that is something that kind of helped Netflix to maintain that industry leadership by quickly adapting to the consumer trends, latest technology, maintaining a serverless kind of an architecture. So they were able to reduce the amount of investment that has to be done from a physical hardware and then just have everything co-located to cloud. So that is one very good example of how an organization has really transformed by moving away from the on-premises hardware and then having the data completely residing in cloud. So without any delay, let's get started with some of the challenges, what we typically see with the data on a day-to-day basis. What is the whole cloud data engineering about, and where do we stand today, right, across globally? So if you look at some of the metrics here that I had, so approximately 463 million terabytes of data are generated globally. And this data could be from various sources like video, text, audio, streaming content. It could be various number of sources. As you can see, it's 463 million terabytes. And this continues to grow exponentially, right? So this data explosion challenges traditional data management methods, prompting businesses to seek advanced cloud solutions for effective data handling. The global cloud computing market is predicted to reach around 2.84 trillion by 2030, which is less than a decade, like half of a decade to put it precisely. This kind of highlights this urgent demand for robust data solutions. With the recent trend or with the recent increase in the usage of social media like Twitter, Facebook, Instagram, Talk, all of these different platforms that widely demonstrate this data explosion. They generate and process vast amounts of data, and it could be on a daily basis, on an hourly basis. It would basically go on what's basically trending. The data would exponentially increase within an hour or within a day. And also, that is just one given use case of how the social media platforms react to it. But we do also have like several healthcare industries that kind of heavily rely on the cloud technologies to manage the different patient records, apply some AI on top of it to and as well as big data. AI has recently started, but I wanted to emphasize both on the AI and the big data side of things, where most of the patient records are managed very efficiently. And also there are many predictive analytics or predictive applications that kind of help to improve the patient outcomes and also to streamline the operations. Now, the other business line that we're going to talk about is also on the financial institutions. So can depend on several cloud solutions to predict the real-time fraud, risk management, and also the transaction processing. So let's take an example for one of the large-scale organizations like Capital One, which has a very huge base over AWS. As we went through three different business lines, healthcare, financial, and as well as social media. This kind of extends across multiple sectors. What I have given is only a bunch of examples and sample, kind of bunch of examples, but it extends to multiple sectors. This would basically empower the organizations to turn data into actionable insights. Maybe they could build some dashboards, they could build some analytics, or they could build an application such a way that takes a preventive action against it. making the decision effectively and driving the innovation as well in wherever areas as applicable. So that is the main reason why embracing the cloud technologies becomes like really critical for businesses that kind of seek sustainable growth and operation efficiency in a data-driven organization. So most of the organizations, I would say, in the recent times, even if you take the large Fortune 500, most of them are data driven. I think that's how most of the large scale enterprises are expected to be seen, that they're data driven. And that's where the whole operational efficiency and everything comes into play. Now, let's also go through in the next slide on how we wanted to see infrastructure aspects of it, like how this whole thing had started, right? So we're gonna, when we go back to the old days, it was basically when even within my organization, if I were to procure a Linux server, someone has to build a VBlock for it, allocate some memory for it. There is a human effort that is technically involved in such a situation. And it could take anywhere from 4 weeks to 8 weeks, right, for a physical infrastructure to happen. Now, when this whole cloud computing had started, the infrastructure as a code revolutionized how infrastructure can be built. So the traditional infrastructure management by providing automated infrastructure provisioning through programmable scripts like Terraform, for an example. So Terraform primarily focuses on having the infrastructure as a code, automating the builds and everything. So the main good part or the revolution that infrastructure as a code has really brought in, it would really transform how businesses manage IT resources. Implementing ISC would also reduce the need to physically deploy something, the amount of time that is needed to deploy, and also minimize the number of configuration errors or human error prone mistakes. Now, there could be still situations where when someone is doing the ISC code, basically someone could make a programmatic mistake, but that's where we could basically do some peer reviews. We can basically have some checks against what we are trying to do, and then basically detect all of these issues beforehand. Another example is also the AWS CloudFormation, enabling enterprises worldwide to automate consistent infrastructure deployments effectively across multiple environments. If we go back to the previous slide where I was talking about Netflix, so Netflix similarly utilizes ISC to manage thousands of cloud servers globally, because it's not truly possible when you have a bunch of servers that are lying across globally in different regions, in different zones, and keeping a tab of them unless it is truly automated and is fully code driven, which is the ISC. Now, it also helps to significantly enhance the disaster recovery capabilities, reduces the system downtime, and fosters better collaboration among technical teams. So, one good example that I can provide is in our organization, at least, we have basically seen a use case where the most of the infrastructure code is already ready. We would just prepare a JSON and submit the JSON to the code, and it would build out a server for us. So that's truly the innovation of how infrastructure as code has brought in. That's truly a revolution that really happened when we go back in time and look at how traditionally things were done versus how infrastructure as a code has evolved over a period of time, right? Now, let's talk about modern data pipeline architecture. So for the modern data pipeline architecture, we know we have like different forms of data. We have different forms of data formats. Either it could be CSV, it could be XML, it could be JSON. The very beginning need to look at the data pipeline side of aspects is to consider that we would have to efficiently process different types of data formats getting ingested on a continuous basis. So let's go through a couple of examples where I can walk you through a very good example of data ingestion, and as well as the processing, the transformation, the storage optimization, the analytics, and the consumption. So let's take one single platform as an example. So I want to pick Snowflake for the purpose of when we start developing a Snowflake application, we would need an underlying cloud storage platform. Let it be AWS, GCP, or Azure. It doesn't really matter. But for our discussion, we're going to consider AWS. If I have 5 different applications that are dumping data into an S3 bucket, which are of different data types, and I want to build something that would technically processes the data in a real-time format, right? So that is where all of this data would essentially come in as real-time as possible from diverse sources with scaling opportunities and capabilities as well. Now, the data that has coming through as part of the data ingestion that has to be processed, that has to be transformed. So we would apply whatever business logic or implementation that is applicable, and we would basically go about running transformations accordingly. Now, that is one very good advantage of how cloud data or cloud data engineering solutions will help us is we're not restricted to any compute. We would basically have a lot of auto scaling of the warehouse size, auto scaling of the instance size. So we're not worried truly about, okay, I'm going to hit about a 50 million users within the next minute. Now I have an on-prem infrastructure. I don't think my on-prem infrastructure is going to handle it, right? So we would technically procure another 3 or 4 different servers and then just have them idle sitting out there. But in the case of cloud, the instances were auto scaled to whatever size it needs to be scaled, like from extra small to an extra large in the event the demand increases, and then scale back down, right? So end of the day, the main goal is to bring in business efficiency in terms of how we are operating it. And if the scalability brings the bridge between the user demand and the business efficiency, I think that itself, the cloud data engineering from AWS as an example, it does a great job. That's the real benefit and advantage of the modern data architecture pipeline. Now, we're also going to talk about storage optimization. The storage optimization, technically, there is no retention period, there is no cleanup that automatically happens on our on-prem storage systems. So typically, we would end up doing like just store the stale data over and over a period of time, and there's no controls or restriction around it. So that is one big drawback of having an having an on-prem system. But then with the cloud data engineering, with the multi-tier architecture, we could have that automated data movement by looking at some of the patterns that are really impacting. And the most important thing is the analytics and the consumption of the data. So we could get like different sources of data, kind of data transform, have business logic applied to it, feed the data into a Power BI dashboard or any analytics dashboard that whatever the enterprise plans to use it, and then technically generate analytics out of it. So this would also reduce the need for writing custom scripts or custom data. So in if I were to go back in time and basically see, someone would have to write a custom script to basically see to generate those charts. And for analytics and to run SQL queries or run any kind of data operations, the data analytics is going to really play an important and crucial role, especially for the financial organizations, as I mentioned the use case earlier. So it's going to actually bring out a lot of value add. Now, elastic scalability benefits. As I was talking about the scalability in the previous slide as well, I'm going to cover this quickly because I went through a little bit deep previously. Resource optimization, having the dynamic allocation, ensuring the perfect resource to workload matching. This is the Netflix use case that I was talking about. The users can increase in any minute, going from 100 users to 1 million users. So the resource optimization is the prime benefit of having the scalability within a cloud data pipeline. And there's also a significant reduction in cost because most of the instances are all on demand. So technically, we could scale back to the lowest server as possible. And for most part, all of the servers are like very pretty high available. They have a very good availability because most of the cloud platforms have a dual zone for deployment setup. Like for example, if I have a server in US East, I would also have a replica in US West. So if the server in the US East goes down, I have a US West region that is really available and really, switch over the region and then give that seamless experience to the user, right? So those are mainly the elastic scalability benefits. Now we're going to go through some of the machine learning operations and how MLOps acceleration can be achieved through the cloud data pipeline. In a typical machine learning application or the life cycle, we would need to have a model that we would develop. The model would be continuously improved upon based on user feedbacks and user inputs. And we would also have to do some monitoring around it to track if the model is deviating from any kind of responses, ability to do the continuous integration. Let's take a use case where I just want to get some data generated through machine learning. Technically, what are the different steps that we go through? We need a model. The model has to be developed, and it has to be developed, it has to evolve, it has to grow, and it has to get the feedback that it needs to get for the model to operate efficiently. Then we would go into the continuous integration aspect where it will be integrated into multiple sources. And also we would also enable like automated testing, which will basically improve the model's efficiency and quality and the reproducibility. Then the deployment of the model itself. Now, typically, as with any other software lifecycle, we would have a test environment and a deploy environment. And the deploy environment or the production environment, and production environment is something that we truly really roll it out to the user. So that's a deployment. And the monitoring, of course, how the model is behaving, how does it act in terms of the different data flows that are coming in. So how does this all tie up to the cloud data engineering as a whole? Is basically most of the cloud platforms today, right now, they have inbuilt integrated MLOps capabilities. So MLOps is an area where it is combining the machine learning and the operation software together. So it gives a great deal of advantage for folks who are truly interested with the MLOps development or defining the models as such. Now, as much as everyone would be interested in moving to a serverless architecture with less maintenance and everything, the other main aspect that also truly really plays a role is how secure are these cloud environments, right? Because we are truly relying on based on the consumer versus a producer, or if something's developed in-house as well, we're depending upon not in-house, which could be the case for an on-prem environment, but we're depending over the cloud, which could be a third-party provider. Now that kind of brings in a very good aspect of discussion, which is about the security. Now, we could basically have, a couple of options here that we could expand upon how the cloud security can be enforced, can be made resilient, and can be made better. So one of them is the AI powered threat detection. We could develop like machine learning algorithms that basically identify and as well as neutralize the accuracy, reducing the security breaches. So typically, the model or the machine learning algorithm gets fed of all the different possible scenarios around the different threats that are really the different threats that could occur. And the model is continuously monitoring the security. The model or the application would continuously monitor the threats and the application with as much maximum accuracy as possible, thereby reducing the security breach, right? And the second option is we could follow a zero trust architecture. This is basically for a very strict identity verification for every user and device, regardless of network position or resource location. We have two-form factor authentication, multi-form factor authentication. We have ping set rate authentication, where users would get an immediate notification whenever they're trying to access any network objects or any different application. And every time, whenever a user tries to log in, it is always continuously authenticating based on the requirements set by the organization. So that is where the zero trust architecture comes into play. And then the third aspect is the compliance automation. These are the intelligent systems that kind of continuously monitor, document, and also enforce regulatory requirements across multiple jurisdictions with minimal human intervention. So I'll give a classic example of how this gets played in a financial institutions such as post-trade brokerages or post-trade event reporting organizations. They basically have a very huge need to comply with the regulator laws and the regulator requirements. Often, when we are sending the data back to the regulators, it has to be continuously the sent back in a continuous feedback loop. And for most part, the regulators would ask for how strong the security of the application is, how strong the network is, and things like that. So this also falls under that compliance automation thing where we could build some intelligent systems that kind of take care of identifying the cloud data pipeline. Now, moving on to the next one, we're going to talk about the intelligent storage management. So, with the storage management, for a traditional storage, we would just have a solid state device sitting somewhere on a rack or a V block or something. But in the in the case of the cloud platforms, it kind of falls under different brackets or different ways. So there could be auto tiering of the data. The data can be classified into different tiers, something that would change frequently, something that would be stagnant for a longer period of time, or something that is like a hybrid. Most of the modern cloud platforms leverage the storage optimization techniques that significantly reduce the cost while improving the performance, right? As I was saying, if some data is prone to change pretty frequently and we don't need the data over a period of time, we could set up retention policies again instead. If we need some data to be available for a very long extended period of time, let's say 2 years or 3 years, like a classic example of Netflix, that is where we could use glacier type of storage where the costs are significantly low, but it is not highly performant or anything. That's one of the catch that typically that we'll have to keep in mind while dealing with long retention data timeframes. Now, if you look at the whole graph here that I'm showing, the data basically demonstrates how implementing a comprehensive optimization strategy combining auto tiering, compression, and as well as intelligent data placement, it would effectively reduce 30% of the cost reduction when compared to traditional storage approaches. So this would also increase the data accessibility and the performance. As I was stating earlier, based on the use case, what we're trying to do, it is really important on how we structure, how we tier it, and how we compress it. So that all comes into play. We're going to look at some of the computing advancements, especially the edge computing advancements. Now let's look at a couple of aspects here. Before the edge computing, the data travel long distances to centralized cloud infrastructure. There used to be a very high latency that compromised real-time applications, server bandwidth constraints, limited scalability, and transmission costs primarily. Now, after the edge implementation, every single data processing that is happening, it is happening in the local network. So let's say if my data center is sitting in London, which is EU Central typically, if we go by the AWS world. Now, if I have something as a data center that is sitting in London, my data has to transfer the network hops from the US to over the internet to the London's network, which could basically bring in a lot of latency. But if I have a data center that is located like in the same state, in the same region as well, then it's going to basically get the local network perimeter, the data access is faster. Now, in correlation and to attest to the fact, it would have an ultra response 15 milliseconds latency, which is like super low, that enables the time critical operations. So let's say I want to do a credit card transaction. Now, credit card transactions cannot run for 5 or 6 seconds. So it has to happen instantly. So that is where having the edge computing advancement will help. And the transmission costs are reduced. It has an optimized bandwidth utilization that improves the network efficiency as well. Yeah. Now, the technology convergence impact. So let's look at three different aspects here. We're going to look at the operational excellence, the enhanced compliance, and as well as the innovation catalyst. So 90% of the faster data processing through seamlessly integrated cloud technologies, it would enable real-time decision-making capabilities, right? So this was the data pipeline use case I was talking about, where you could get the data from different sources combined together, have a centralized data transformation, data application, whatever we're trying to do, and then basically improve your business operations and business efficiency. Now, the second part of it is the enhanced compliance, which kind of falls under the automated governance and the regulatory adherence through the entire data cycle. And the third one is the innovation catalyst, acceleration the time to market for data-driven products, creating sustainable competitive advantages. So let's take an example of the social media platforms. So let's say there are 2 or 3 of them. Now I want to build a fourth one. We could use a mix of machine learning. We could use a mix of something as well as architecture and have everything deployed in no time, right? So it accelerates what the business really needs in a very short span. And also, as far as the costs are concerned, we're not paying anything upfront to procure the infrastructure. And we're also saving a lot of time for a fact. So let's say I need like about 20 different V blocks and a whole bunch of network routers and everything. I would end up dealing with a lot of infrastructure teams waiting and paying for the cost, even when I'm not really using them. So that is where the innovation catalyst comes into play, where most of the acceleration in time to market for data driven products or data driven applications, it really speeds up because it's all cloud driven, cloud data driven, and cloud infrastructure driven. Now, someone could question back saying, how do I really make a move for an application that is sitting in a legacy environment to cloud? So I think it is really important to do an assessment of a very comprehensive analysis of the existing data architecture. How is the data flowing? Is your database on-prem? Are you using a database? Do you need some local storage? Do you need the cache? How's the performance looking, and what exactly are we trying to achieve with the current application that we really have? That comprehensive analysis of the data architecture, underlying performance gaps, and the high value optimization opportunities through the stakeholder interviews and system audits is something that really needs to happen. Now, that serves as a foundation, as a basement to get started. And based on that, they would go about moving into the strategy development aspect, get some strategy flowing around it. What type of cloud platform do you want to use? Do you want to go with AWS, GCP? Do you want to go with a cloud driven database? How do we deal with the data? How would your data pipeline be built? Get that strategy going and get an estimate of the cost that might incur as part of your strategy. And also look for what is the net value realization that you're getting out of the cost. So let's say if you're spending $1 million today, that's for an year. And then if you see that your cost could be reduced to 150 grand for every year, then yes, yeah, that would be an absolute use case why we would want to move to cloud, right? So getting the strategy development, designing cloud, customized cloud migration roadmap aligned with business objectives, including the technology stakeholders, governance policies, and also the regulatory compliance and implementation timeline. And with the actual implementation itself, we would need multiple teams to get involved, get the cross-functional teams, leverage DevOps. How do we do infrastructure as code? How do we code deploy to AWS? How do we bring down the instances or get the regular infrastructure support aspects as well, the DevOps methodologies, and also establishing the feedback loops for continuous refinement and capability building. And as I said earlier, the value realization, what is the cost effectiveness that this is going to bring us in terms of moving to cloud? So that basically summarizes the data transformation journey. So that's pretty much I had. I hope you all felt interested in what was spoken so far. Please feel free to reach out if you have any questions or any clarifications. All right. Thank you.